Okay, I'm going to spend a few minutes going through Chapter One's lecture slides. Okay, and primarily it talks about introducing to the field of engineering and kind of where engineering analysis fits into that. Okay, very brief overview. Okay, so engineers are people that solve problems. Okay, so um, they solve them in a formalized fashion, and they apply well known and well established theories and practices to do that. Okay, different types of engineering careers or engineering fields or disciplines. Mechanical engineering is one. This is where you're actually dealing with physical systems, physical objects, and you can use this in different things: manufacturing, maintenance of systems. You'll see this in a lot of different industries. And you see a lot of crossover between the different engineering disciplines to actually go through and design a system. And you have civil engineering and civil engineers are dealing with, basically structures, right? Building structures. It's roads, bridges, buildings. Seems like there's going to be a lot of demand for that across the country, especially in Connecticut with the state of a lot of the bridges and roads in the state. Okay, electrical engineering. So this is using electrical and electronic engineering principles. So you can see that, any kind of relatively complicated system are going to require, multiple disciplines to solve it, whether it's, aircraft, ship, computer, uh, television. All these things require multiple ones, okay? But they're, electrical engineers' primary focus is electricity, electronics, um, power. Power is included in that. So power distribution, power generation, electrical power distribution is all part of that. Even telecommunications. Okay. There are other ones out there, of course, aerospace, software, industrial. And if you want to, you can go out to this link and check this out, for different engineering fields if you're not decided at this point. So it gives you kind of a broad spectrum of different engineering fields and provides a little bit of information on each. Okay. So here's engineering design, right? So this is, you don't have to memorize this or, um, um, we're not necessarily going to follow this all the way through. We're actually going to go through and do analysis and analyze the systems, use math for the most part to analyze systems. Okay. But this may be a typical way, you have some objectives, you go through a design strategy, gather information, make a first attempt, you build a prototype, right? So in this case, you have some prototype of your system, whatever it is, you document, you have some testing that goes through. If it doesn't meet the specs, then you go through some revision and go back and go through the steps again, okay? So if it does meet the specs, of course, you do some final testing, and if it meets the specs here, then it can actually go to market. Okay, so this is a very, it's a flow chart that's very general, kind of give you an idea of going through it. So we're in here somewhere, it's like the gathering information, make a first attempt. So you have your mathematical models in addition to, but you use those to help with the design process. And then from that, of course, you'd build a prototype. But we're kind of in here. Okay. So design process. Okay. So these are some of the things when you're going through the design process. And like I said, um, you know, we're not going to necessarily go through all the design process, even though kind of presenting to you at the beginning. Okay. So steps. Here's some steps to design the components. And when you make decisions on things, it's these are some of the questions you need to ask yourself, right? Is it cost effective? Can you build it? Will it work? Is it needed? Right? Is it needed? It's probably the first one. And just as anything else, you make decisions, right? It's engineering. You have trade offs, okay? And so you make it based on math. So like theoretically, will it work? And any science principles and concepts, ethics, and then economics, of course. It's like it's always some kind of trade offs between well, it could be economic safety. It could be um, reliability based on You can make something almost completely safe, completely reliable, but it may cost. What's the cost? Maybe in very, very high cost, so it would put it out of a reasonable thing to do. Okay. Engineering analysis. Okay. So this is what we're looking at, right? This is kind of the main point of this. You're breaking down a problem, right? And what we're going to do is we're going to use mathematics, principles of science to analyze the system. Okay. All right. Design and failure. And so you could think about analysis as probably as a prevention tool, right? So it's like, will it work? Will it support? Like if it's a bridge, will it support the weight that I expect? Will it be able to stand in the wind? Can it handle the wind against it? Can it handle different forces at different areas? Would it withstand like a mild earthquake or, you know, if it's a bridge over water, if the water was a flood, could it handle the flood? So there's a lot of things that um, we can do with analysis. All right. Another one is learn from our mistakes. Okay. And there's a video that you can watch, Tacoma Narrows Bridge, which can show you kind of that whole process there, which I have a link to a little later. Okay. So sometimes are failures acceptable? Well, failures happen, so you have things to protect it, like fuses are used in electrical wiring so they don't overheat. So you blow the fuse instead of melt the wire, or melt the insulation at least, and then melt the wire. Um, so fuses are in a failure case. Car bumpers, rear view mirrors. Like, yeah, you better have rear view mirror so you're moving over. So if somebody's there. Motorcycle helmet, really useful for if you get into a crash, right? Breakaway collars and lighting poles, right? Some of those lighting poles and signs will break very easily if a car hits them instead of stopping the car dead, right? In its tracks. Okay. All right. So here's an interesting example just to give you an idea of what kind of decisions, have to be made. And it has to do with the Ford Pinto, which is no longer around. Um, but basically, here's a process. This is a kind of an interesting example. 1971, they needed a car. Ford wanted a car, weighed less than 2,000 pounds, and cost less than $2,000. Okay. So they came up with a Pinto. And this one, you know, size and weight, initial price, reliability, fuel consumption. Okay, so relatively low cost and product appearance. Okay, well, that's always a relative thing, right? Comfort, features, handling, performance, right? Does it meet the specs or design goals, right? Okay. Well, after, deploying the car and having sold it for a while, what they found was that uh, in crashes over 25 miles per hour, you ruptured the gas tank. Okay. In addition, what it did, it buckled so badly at 40 miles per hour, you couldn't even get out of the car, right? So you could be trapped in a burning car. Well, this is one of those economics decisions, ethics and economics. They figured out it was easier um, to pay, or at least they estimated it would be easier just to pay off people than going in and making a fix that was only like $10 to $15, right? Okay. What they found was that the cost of the accidents were underestimated, and that 500 people essentially burned to death up to that point in 1976, right? So of course this car is no longer around, right? But you can see just from what companies do, or what people are required to do, is they make sort of a cost benefit analysis of what decisions you use that as part of their decision making process. Um, but it's an interesting example. So here's just a Pinto design flaws, and they talk about that after the analysis was done. They figured out what were the issues here and what you could do to actually mitigate it. Right. Another one is a famous one is the Tacoma Narrows Bridge, and there's videos on it. This is a link to a video, and you can go and watch that, or you can go on YouTube. It's on YouTube. You can go watch that, and you can find other videos on YouTube if you just search for that. It's an interesting design failure, and it actually, in terms of bridge engineering, it helped bridge engineering advance quite a bit. Not from initially, but after, from learning from the mistakes that they made. Okay. And so that's pretty much it, for chapter one's lecture slides. Okay. So pretty basic this time. In general, what you'll see is that, I'll go through the lecture slides and I'll also work on some engineering problems, right? So this is just a kind of a brief overview of kind of engineering analysis, what it is, and kind of a simple example or a couple of examples. Okay, and that's good.